Hello AP Physics C students, are you ready? Because this is going to be a lot. Here we go. Have your notes open. Go ahead and read this slide. A lot of information going on here. Okay, so now we're combining an inductor with a capacitor. Here we go. Close the switch. There's all this energy stored up in the electric field of the capacitor, and then the capacitor tries to discharge itself, but of course remember the inductor doesn't like changes in current, so let's see what happens. Using Kirchhoff's loop rule, the charges flow around this way, we're going to go this way, so we're losing voltage. Delta V is negative here, so negative Q over C, and we're losing voltage here as well, negative L di dt. Okay. Read, pause, come back. Yeah, right. So the capacitor is losing energy. That means the inductor is gaining energy, storing up energy in this magnetic field because the current's increasing. Here's our equation rearranged. Wait a second, right? di dt, that's the first time derivative of current, is the first time derivative of current, but current itself is the first time derivative of charge. That means this is the second time derivative of charge, right? Q, current is dq dt, di dt is d squared q dt squared. This is the second time derivative of charge. That looks awfully familiar, doesn't it? If I divide everything by L, and here I'm using lowercase q for the time-dependent q as opposed to capital Q, which is like the total charge on the capacitor. This equation looks awfully familiar, doesn't it, right? Should really jog some memories. Looks just like this. Wait, what's that the equation for? Simple harmonic motion, you say? Mass on a spring? What? What? Yeah, remember the solution to this is an equation for x that looks like a cosine function, some amplitude times cosine omega t, where omega is the angular frequency, and omega squared is this term here. This is the condition for simple harmonic motion. So by inspection, that means we can get an equation for charge with respect to time that follows the same pattern, whereas this is the maximum position, this is the maximum charge on the capacitor, cosine omega t. Omega squared then must be this term, 1 over LC, just like omega squared was k over m here. So omega itself is the square root of 1 over LC. This is getting weird, but let's continue, right? So here, when we did this for simple harmonic motion, we took the first time derivative of position. That, of course, is velocity. So that's going to be the derivative of cosine, which is negative sine. Then with the chain rule, that's the derivative of the inside, which is omega, so negative a omega sine omega t. So over here, when we take the first time derivative of charge, that's going to be current. That means we should be able to get an equation for current by taking the first time derivative of this. Go ahead and do that on your own. We should have got an equation that looks like this, right? Derivative of cosine is negative sine. Chain rule omega, so it's negative q naught omega sine omega t. So that's how it's the same form as this. You'll recall this is the maximum speed the mass was going at, right? When time is pi over 2. And so here, this represents the maximum current going through, q naught omega. Let's box in some equations here. Here are the important equations. This is the charge versus time, the current versus time. Here's our angular frequency for this LC circuit. Okay, pause, read. Okay, so watch what's happening, right? The capacitor starts fully charged. It's going to try to discharge itself by pushing charge this way. So there's a current here. Now the current builds up inside the inductor. When current builds up inside an inductor, UL equals 1/2 Li squared. That means it's getting magnetic energy at the expense of this losing electric energy. Pause, read. Yeah, this is where it gets interesting, right? And so if the current keeps building up more and more, even when this gets fully discharged, the current keeps going past this equilibrium state, so the charges keep flowing, and the positive charges end up on this plate. This plate starts becoming more and more positive, leaving this plate more and more negative, and that means that the capacitor is now getting charged in the opposite direction to what happened before. I hope you're taking good notes on all this, drawing pictures of all this, right? Take good notes. So at this point, when the capacitor gets fully charged the other way, the charge momentarily stops, but it's going to start reversing direction. For some reason, I think it repeated all that stuff over here. Pause, read, come back. Right, so now this capacitor is going to try to discharge itself this way, forcing charge the other way. Here's our oscillatory motion. Okay, so at this point, we're making all these analogies between this LC circuit and a mass on a spring. So what I want you to do is, if you haven't yet, download and print the notes pages. This page here is going to do a comparison between a mass on a spring and an LC circuit. Everything plays its own role. It's like a theater production here. So I want you to look at what we've done so far. Pause the video. I want you to fill in as much as you can. What terms are playing what roles in each of these different situations? See if you can line it up with the equations and think of what's happening with the charges going back and forth between capacitor plates on one side and capacitor plates on the other side, and then come back and I'll lead you through it. Okay. So the first thing here is charge. Charge is clearly playing the role of position. Look at the equation, x equals a cosine omega t, q equals q naught cosine omega t. They follow the same sort of pattern there, and so it's a little bit weird, but the position of the mass on the spring is playing the role of the charge on the capacitor, right? Okay, so the next thing then, if this is x and dxdt is speed, that means the qdt has to be current, which is playing the role of speed, right? Each one is the first time derivative of the original. The xdt, the qdt, current is playing the role of speed, and that kind of makes sense. I mean, we certainly used current as sort of like velocity before. Okay, so then we take it to the next level. The first time derivative of speed or velocity is acceleration, so then di dt has to be acceleration. Right? The second time derivative of charge is the second time derivative of position. So di dt plays the role of acceleration. Okay? Alright. Where should we go next? Oh, inductance is playing the role of inertia. That was sort of alluded to in some of the notes slides before. If you weren't sure, maybe you want to go back in the video and see that happen, right? Remember, inductance resists the changing current. It's not exactly the same thing, but it's playing some sort of inertial role here. And so it's sort of playing the role of mass, which is like inertia, right? Mass, it resists changes. So now watch what happens. Here's L, which is playing the role of mass. Here's di dt, playing the role of acceleration. This looks like ma, which means this must be sigma f equals ma. That means that EMF is playing the role of force. In this case, it's like the spring force, right? Because, of course, we're comparing the LC circuit to a mass on a spring. This is sigma f equals ma. The EMF is playing the role of force. Okay, now let's talk about some energy stuff. All right, so inductance plays the role of mass. Current plays the role of speed. Here's 1/2 Li squared. That's like 1/2 mv squared. That's kinetic energy, isn't it? How many of these are you getting right? Okay, all right. Let's look over here. Well, if this is kinetic energy, this is the only other energy. This must be spring potential energy. This must be 1/2 kx squared. All right, well then the x, that's the charge. That makes sense. There's the x squared. There's the 1/2. What's this thing left? Oh, it's got to be spring constant. So spring constant is playing the role of inverse capacitance. Sorry, that doesn't help very much, but at least everything lines up. Okay. Okay. How many of these did you get right? Hope you got a lot of them right. Okay. Now, with this in front of you, we're now going to go into a really detailed analysis, step by step, of the mass on the spring versus the LC circuit. But I think I'm going to run out of time on the video, so I'm going to make it into a new video.